Good morning. I'm going to give you guys about 10 minutes to work through these, and then we will go through them at the class. All right, let's get started. I'm gonna rewrite them on another page so I can go through them a little bit more thoroughly. Start with this first one. All right, we are going to start by picking off one of these protons in our beta position to form an enolate. From here, we can interact with another equivalent of our starting aldehyde. So our electrons come down, reform our carbonyl. Attack this aldehyde over here. Form a bond between the carbon at the end of our double bond and our carbonyl, so it should look like this. We can pick up a proton from that water. And then we can pull off this proton using our NaOH in solution and heat. So pull off this proton, make our double bond, kick our electrons out to our oxygen. Oxygen can come grab the other proton here. We will form a conjugated system. That should look like this. All right, next one is a ketone, which makes it a little bit different because we got to deal with selectivity now. So we're in NaOH, which is a small base. We're just going to make this selective for our secondary position over here. Which means we should form this enolate. Who can interact with another equivalent of itself. We can pick up an H plus. Do the same thing we just did. To get our product. Which should look like this. All right, let's do some brominations. First one should be a simple bromination. We've got an aldehyde here. We can form our enolate. This can come down to form our carbonyl, attack our bromine, allowing us to brominate at that beta position. If we do this with a terbutyl on one side and a primary on the other side, like in the next problem, so NaOH, Br2 in excess, we are going to be able to make, so we're going to tribrominate off of all three of these protons here. The other side doesn't have any protons, so you can't form an enolate on that side. From here, this is a pretty good leaving group, so water can come in, displace this CBr3, and we're going to form our carboxylic acid. I'm gonna skip the next one, do that one last, the one with 4 products. I'm gonna do the bottom 2 ones next. Going back to some more aldol condensations. So for this one, we're using a large base, LDA. Which means we are going to selectively deprotonate from our less substituted position, which would be this primary position. From here, we add in another aldehyde to attack. So the reaction gives us this ethyl aldehyde here. We can reform do an attack on the center. We're going to create originally. Our negatively charged adduct can pick up an H. To what would actually be the product for this reaction? I didn't actually draw heat for this one. This is technically your product. If you were to add in heat, I'll show what that gives you, just so you guys have that. So if you were to add in heat, you can eliminate and form your double bond. But based on what was drawn, this would be your product down here. All right, last one is actually going to give you one product no matter if you add heat or not, because you're going to end up with a quaternary center. So we have a small base. Which means we're going to form an enolate here. I guess that kind of works. It looks like I gave you something to attack, which is another ketone. So these electrons should come down. Do an attack on this carbonyl center. We're going to make, I'm going to kind of flip this over. Originally this, which will pick up an H to give you your product. And the reason that this is going to be the only product here is that there's no protons in this position. So even if you were to add in heat, there's nothing you can actually eliminate there, because the other positions aren't going to be acidic enough to actually do a condensation. You really need to be conjugated in order to get that to work. So this is going to actually be your end product from this. All right, let's do the one with 4 products. We've got 2 different aldehydes plus NaOH and heat. So each of these can form an enolate. I'm going to draw them both twice. These are going to have 2 different partners they can interact with. So for this first one, if it interacts with itself, it should form through a condensation reaction, something that looks like this. So we have one equivalent here, our other equivalent is made up of this. If it interacts with the other starting material, it's going to be very similar. We just have one less carbon here. So our product should almost be identical. For our other side, if this interacts with our other starting material, so we don't have this carbon anymore. We now have an extra one, or we have the same one over here. So it should be almost the exact same product as this, just without that carbon there. And then if this last one interacts with itself, this can, sorry, be the exact same product as this. We're just going to have one less carbon here. Giving us this. So it's always the same reaction happening. You're just kind of taking and removing carbons. All right, so I'm going to talk a little bit more about the Claisen condensation and specifically ring closing reactions. For the sake of this class, your ring closing reactions are only going to really form as either 5 or 6 membered rings. Three, 4, 7, 8 don't really happen. So with that in mind, let's take a look at a problem. So if I were to do what I would normally do with this, I have NaOH, small base, going to attack the more substituted position. They're symmetrical, doesn't matter which side you pull off. I'm going to use this left side here. We can make an enolate. This is going to try to close. Whenever you're making a ring like this, your ring size is going to be the number of positions between this end position of your enolate here and your carbonyl. So this would be 1, 2, 3, 4 carbons between them. So it's going to make a 4-membered ring here. So if we were to draw this out, this would give us I'm going to pick up that H. This. So it's a four-membered ring, which is most likely not going to happen. They're just too hindered to actually form. What's more likely to happen in this case is that we're instead going to pull off one of these H's that are on the end. Actually, I can just draw this anyway. And form this enolate. And the reason behind this is that when you do your attack here, we can make a much more favored ring. So now we're making our ring from the end over here. 1, 2, 3, 4, 5, 6. And we're gonna make a ring that actually will form. So 6-member rings are much more likely. If I was to draw this out, it's gonna look so I made a bond between here and here. So we need the methyl that's still there and the OH. And then we should have our ketone still. Am I a carbon off? I'm a carbon off, dang it. There we go, okay. Oops. And then from here, doing the same thing you normally do. So you add in heat. Oh. To get your final product. I'll do one more of them. All right, so aldehyde and ketone. Together, your aldehyde is a lot more acidic. So if you add NaOH to this, on Monday we talked about a little bit of pKa's. So our aldehyde is our more acidic protons, which means these are the ones that are actually going to pull off. We can make these enolates here. We can close to form a ring. So again, we're forming the ring between the end of our enolate and our carbonyl. So this is going to be a 1, 2, 3, 4, 5-membered ring here. Should look something like this. You can protonate. And then pulling off or throwing in heat to do a condensation will give you your final product. So there were some questions in the 930 class about why doesn't this attack itself? And a lot of this has to do with how you run reactions. We don't really get into it much in this class because this is mostly theory and not really like lab-based type of reactions. But if you think about it, like if I had a reaction beaker, oops, and if I ran this at a really high concentration, then it's likely that instead of this forming your ring here, this would just attack another version of itself. Versus if you're running this at a really low concentration, so most of the time when you're trying to do these intramolecular ones, you'll add a lot of solvent and run it really dilute. So if you think about it now when you're forming this aldol, if there's nothing around it, it's just going to attack itself versus having a lot of neighbors. So at low concentration, these reactions work really well. At high concentrations, you get a lot of byproducts. But that's not really something we're talking about in this class. So just in case you guys are curious. Okay, I am going to talk a little bit about the Claisen condensation, which is a pretty similar reaction to the aldol. We're just going to be dealing with esters now. And it'll give you a slightly different product. So if we take an ester and throw in, you're gonna always want to have the same base as your ester group here. If you throw an NaOH, this actually might turn into a carboxylic acid. So if you throw in instead NaOET, on the off chance this does attack your carbonyl, you're not going to lose that OET, you're going to retain it. So NaOET will let us pull off proton. In order to generate an enolate. This can attack another equivalent of itself. And unlike the aldol, where we normally just have an H where that OET is, now we have somewhat of a decent leaving group. So this can kick out this OET, and we're going to make a keto ester here, which is actually our final product. What happens though is that because you're in base, this is a really acidic position here. So your OET is going to pull this off. And then you throw in H3O plus to quench the reaction. And it gives you your final product back. Let's make H3O plus. All right, let's do another one of these. Let's do a methyl ester this time. So we need NaOMe. We're going to form our enolate. OMe. This can attack another equivalent of itself. Oops, that one shouldn't be the enolate. Kick out this ME here and form our final product. All right, we got one more reaction today. It's basically the same as bromination, except you're doing alkylations now. Question in the chat. All right. Take a ketone or an aldehyde, throw in base, followed by some sort of haloalkane. We can make an enolate. Our enolate can do an SN2-like reaction on this propylaldehyde or propyl iodine here. We're going to kick out the I, make reform our ketone, and then add free carbons to this position here. So same reaction we're doing with the bromine. Now we're just doing it with haloalkanes. Same concepts as before for large and small bases. If I had a small base, NaOH. I'm going to selectively pull off this tertiary proton here. Versus if I had a large base like LDA. Can selectively pull off one of our secondary protons. To give a different product. All right, I'm going to stop here for today. On Friday, we will probably finish up chapter 21. So I will see you guys then.